Hi, my name is Michael, and I'll be giving a talk on some recent changes to the way the Go runtime manages memory. The name of this talk is a real mouthful, but I promise it'll all make sense as we follow a single cohesive narrative thread. So why this talk at all? It's a tutorial. I want to help folks understand how some of these things work under the hood and how we got there, and maybe help those more performance-oriented among you to understand the behavior of your program. Keep in mind that this information is valid for the current releases, but may change as time goes by. And I'm going to be talking and focusing more on the goals, policy, and design, more high-level stuff than in the weeds. Though there will be some weeds we have to pull. And hopefully this will be fun. Things went hilariously wrong at some points, and this work was all part of one big journey. One thing I want to point out is that a lot of this stuff is not something allocator experts talk about very much. It's usually a footnote in many allocation and GC papers, not all though, certainly, but turns out to be very important in practice. So here's an outline of the talk. I want to first get everyone on the same page, have the same mental model, and understand what level we're operating at. Then we'll talk about the lowest level of the allocator, talking to the OS. This is the RAM efficiency part of the talk. Then we'll talk about the second lowest level, and this is the CPU efficiency part of the talk. So without further ado, let's jump into some background. So let's start with the concept of a page. It's really at the center of all this. What is a page? Up here on the slide, I have the Wikipedia definition of a page, which is a fixed-length contiguous block of virtual memory that's the smallest unit of data for memory management in an operating system. Let's unpack that, starting with virtual memory. On your computer, we have some physical resource called RAM, which stores your actual bytes of data. All of these bytes have some address, but user programs never directly use these addresses. Virtual memory is a layer on top of physical memory that is managed by the OS and hardware in tandem. The basic idea is that every 64-bit program gets to pretend that it has 2 to the 64 bytes of memory, what we call the virtual address space. No machine that I'm aware of gives the program access to 2 to the 64 real bytes of memory, but this layer of indirection gives the OS flexibility. For example, it can swap some of this memory out to disk, or it could shuffle memory around for somebody who needs it. And so remember how I said that the hardware was involved in all this? There's specialized hardware for managing virtual memory translation because it's so useful, and specifically the translation between physical memory addresses and virtual memory addresses in the virtual address space. A consequence of this is that the length is typically just fixed for a given machine. If you emulate this in software, you can get a little bit more control, but not beyond baking it into the OS image, and variable size pages are just too slow. And so page sizes, to give you a better sense of how big a page is so anywhere between 4 kilobytes and 64 kilobytes, typically a power of 2 since those are easier to work with. And finally, this is the smallest unit that the OS knows how to give out. We can't ask the OS for less than this amount. It's baked into the hardware. The entire address space then is pretty much defined in terms of these pages. You can split up the entire address space into these pages. Okay, so the next thing I want to talk about is dynamic memory allocation, which is what really motivates this whole talk. And so what do I mean when I say that? We have some data and we need to put it somewhere. The Go compiler can't figure it out. Either it would take too long, or there's really no place either in the program itself or on a goroutine stack or something. So what it does is it emits a function call to find space at runtime. That function call is into the dynamic memory allocator. So how do pages fit into this? Well, recall that a page is fixed length and the smallest unit the OS knows how to talk about. What makes this a problem at all is that the data we want to place is often not exactly the size of a page. Sometimes it's smaller, so we want to pack these objects together, objects of data together, and sometimes it's larger, right? And so we want to put our data across multiple contiguous pages. And just to orient ourselves a bit better, I created this layer cake for you. And here we've got the Go runtime at the top 2 layers. And then we have the operating system, and then we have RAM. So actually placing objects is outside of the scope of this talk. but does motivate it. So the top layer is sort of out. Don't worry about it. It's important because this is something that programs do, but we're not going to be talking about that part of it. So to start with, we're going to talk a little bit about the operating system. And we've already touched on virtual memory, so that's why it dips down into the physical memory layer, this little drawing. But we'll be primarily talking about how the runtime manages free pages. And we call that the Go page allocator. We on the runtime team call it the Go page allocator. And to avoid dwelling too much on memory allocator, specifically like the overall design, I'm going to take 4 things as a given. And these are things that virtually every modern day dynamic memory allocator does, and virtues in some sense. The first is that you want to keep some kind of pool of free pages, like completely free. There's no data that the application needs in those pages. The second is that sometimes the allocator wants more than one contiguous page. And a simple case is, someone wants to put several contiguous pages of data together, right? So you have some very large object that you want to allocate. But there are other cases. The third is that you always want to reuse partially used pages as soon as possible. And that's what eagerly means here. Don't wait, make it available as soon as possible. If the application is using only a small bit of a page, we want to be able to make allocations against the rest as soon as possible. Otherwise, you're just wasting memory. And the last thing that we're going to take for given is that once a page has no more data into it that the program needs, we return those pages back to the pool eagerly. And so consider that pages in this pool are in their most malleable form. Often pages are allocated for specific purposes, so making them maximally available when they're done lets us slosh pages between different use cases. I could talk about this for a long time, especially about why an allocator needs these things, but I won't dwell on this since it's more about the design of an entire allocator, and so kind of outside of the scope of this talk. So with this idea of a pool in mind, we can narrow our scope and model the part of the allocator that we're going to talk about like so. And so this is an incomplete life cycle of memory. The Go allocator takes those pages and does a lot with them. But this slide is going to sort of be our home base for the talk. Great. So with that background out of the way, onward to part 2, how the Go runtime interacts with the OS. And so specifically back in our home base, that's this part of it. Note that this arrow between free pages in the OS is bidirectional. So yes, the Go runtime does return memory back to the OS too. But let's first talk about how we obtain memory, because it's sort of simpler and easier to consider. Obtaining memory happens with some kind of system call, like mmap. Don't worry too much about the system calls themselves. Basically, you ask the OS to make some memory in your address space read-write, and on first access, it's going to back it with real RAM. And pretty much every modern OS works this way. To return memory, you also make a system call, but things are a little bit more complicated because there are a couple ways you can do this. One way is to say, oh, that memory region that you gave me earlier, I don't need it anymore, just get rid of it completely. And we could do that, but it turns out that that's kind of slow. And instead, what most OSs give you is a way to say that you don't need the contents of a memory region anymore, instead of saying that you don't need the memory region at all anymore. And so the idea here is that in the future, if you want to reuse that virtual memory space, you can. And there's 2 schools of thought here, and both carry a cost. On Unixy systems, it's implicit. If you touch that memory again, the OS is going to scramble to find RAM for you. So you do a system call, you return that memory to the OS, and then later you read or write, or probably not read, but you write a byte to it. And the OS is going to be like, oh no, there's nothing backing that. There's no physical memory backing that memory region, so I'm going to go find you a page. And it's going to zero it out, make it ready for you. There are some notions of lazy freeing in this world where the OS will only take back the memory when the whole system is under pressure. And if it does take it back, then it will do the same sort of scrambling I just talked about. If it if the system is not under pressure, then it'll just give you back what's already there. It makes no guarantees. And it also updates some bookkeeping just so that it knows that that is in use again. On Windowsy systems, it's explicit. So if you try to touch that memory region after you do a system call that says, I don't need the contents anymore, you're going to fault. The OS is going to say, no, you can't actually touch that. You need to do another system call to make sure that you can reuse it. And I say Windowsy, but also macOS has a method of working this way. It actually supports both. Okay, great. So with the basics out of the way, let's talk about policy, specifically the what and the when, starting with obtaining memory. So the what is kind of abstract, but I think it'll become more clear as I talk about it. So let's start with a simple question. When do we obtain memory from the OS? And this is pretty straightforward, just when we need more. We've exhausted all the memory we've already asked the OS for, and we need some more, so we ask it for more. Straightforward. The question is, what memory do we want? And really, we don't care. It's nice if it's contiguous with the memory we've already asked the OS for, but don't worry too much about this. Robust allocators can handle it being discontiguous, and the OS also has heuristics that mostly does this for us, and the details around this aren't terribly interesting. Returning memory to the OS, on the other hand, is a complete enigma. Everyone seems to disagree on how to do this and when to do this. And so as a starting point, let's see what Go did for a very long time. Here's a pretty simple solution. We know there's a cost to returning memory to the OS. So let's avoid that cost by only picking pages we're pretty darn sure aren't going to be used again. We track how long each page is that's managed by the runtime, how long it's been completely free and unused. So, the application hasn't had to store anything there. Then every few minutes, we'll walk over the whole heap and return whatever's been unused for a long time to the OS. And so note that 5 minutes on a modern CPU is an eternity. So this is very, very safe. And this is what Go 111 and earlier did. Of course, this has problems. The most pressing one at the time was that what if all that free memory is fragmented and we get some new large allocation that doesn't fit? So you can see in this diagram, we have some notion of the heap. The light blue regions are free. The gray regions are currently being used. And the dark blue regions have been returned to the operating system. So we have this new allocation request that comes in, and if we shuffled the memory and put it all together, we would have space for it. But in reality, we don't, right? We have no place to put this. And there are reasons why we can't just shuffle memory around, and I'm not going to get into that. But basically, as a result, we have to ask the OS for more memory and then put that new allocation there. And so that's not great, because now we're using a lot more memory than before. So let's see if we can fix this. In Go 112, we added a few additional rules to tackle this problem. First, let's try to do this every time that the Go runtime asks the OS for more memory, in addition to checking the whole heap every few minutes. The idea here is to avoid an out-of-memory condition by eagerly freeing up some of the fragmented memory before the new memory is used. However, we don't want to run over the whole heap because we're going to do this eagerly right when we ask the OS for more memory, and we do that during an allocation, so we're going to be blocking the application while it tries to do stuff. So we don't want to run over the heap every single time because that's very expensive. Specifically the Go runtime, we don't want it to run over the heap every single time because that's expensive. So we need some way to pick which blocks we're going to look at and return to the OS instead of trying to look at everything. And so let's pick the biggest contiguous blocks first. And this nicely mirrors our best fit allocation policy for pages, and more on that soon. There are also some fixed costs to returning memory to the OS, and we can amortize that by returning more memory at once. And an important note here is that in order to make this all work, we had to track the returned and unreturned memory separately. And this meant that we couldn't allocate across the two. In practice, the two should remain largely separate. The biggest concern here is fragmentation. because now you are sort of splitting up regions that you might have been able to allocate into before. But in practice, the theory is that it should remain largely separate because we have such a conservative rule here that it has to go unused for 5 minutes. But remember this point because it's going to be important in the coming slides. So I tried to roll this out to a fairly large Google service to validate that it actually works and that our assumption about tracking this memory separately and fragmentation made sense. So the graph here is virtual address space on the y-axis and time on the x-axis. The blue line is Go111 and the yellow line is Go112. The goal was to see if we could reduce the incidence of out-of-memory errors, but I first wanted to validate that a single instance works fine. And so I watched the graph as the instance process data, and let's follow along. The x-axis is going to stretch out, and as a result, so will the y-axis as we use more address space. And so I want to be very clear that the y-axis is virtual address space. So we're mapping in more memory. This doesn't mean we're using all that memory because we're actively returning it to the OS, but we are this is how much the Go runtime has asked the OS for. Okay, so we go from 30 seconds to 5 minutes, and seems okay. It's using more virtual memory, more fragmentation. Not really a big deal, and not really a big deal because we're not backing it with real memory. Moving forward, well, okay, that's starting to become a lot more. The Go111 has sort of leveled off. We should figure out what's wrong here, but maybe it's not that bad. Oh, okay, that's really bad. I let this run, and it basically had no signs of stopping. And this is like a virtual memory leak in some sense, right? This is like what can happen if you have unbounded fragmentation. Even though we're continuously returning memory to the OS, and that all of this memory isn't actually being actively used, there is still a really big problem here. Because unfortunately, for every 8 bytes of virtual address space, the Go runtime maintains 2 bits of heap metadata for the GC. And that was a problem because that does take up physical memory. We don't return that to the OS. And that's the red line here. It corresponds to the yellow line. And so as that sort of goes up over in time, now your service is going to start to run out of memory. And that's really bad. And we don't return that memory to the OS for various reasons. So this baffled me for months until I wrote some tests for the runtime. And in particular, we need to keep track of free pages somehow in the runtime, right? Remember the pool I was talking about? And up to Go112, we were doing that by managing contiguous blocks of pages, of free pages in a tree. The tree was ordered by size of block, and the way it worked is it would find the smallest free space that would satisfy a page allocation. And this policy is traditionally called best fit. However, in front of this tree was a cache of sorts that held small contiguous blocks of pages for faster access. How useful this was in our case was kind of dubious, and it made doing this work more complicated, so I got rid of it. I put everything in the tree. And that would have worked fine, maybe a little bit slower. In practice, we didn't really see a slowdown because of that. But there was a bigger problem. It turns out that the find operation to get this best fit, to get specifically the smallest free space that would satisfy the allocation, it was just wrong. And so here's a paraphrased version of the code. Don't spend too much time into it. Don't dig too deep into it. Don't try to understand it. I just want to illustrate how if you know anything about trees, this just kind of looks right. I looked over this code so many times myself. Many very smart people looked over this code many times. It went through code review, and yet it's so wrong. It doesn't return the best fit at all. And that causes serious fragmentation problems. It's basically returning like memory at random that satisfies the allocation. And this can have like really bad pathological behavior. So I fixed it. I wrote the unit tests, which discovered this problem, and I fixed it. And if you look at this is the fixed version. It doesn't even look that different. It's all very subtle. And so this is an example where unit tests actually were really, really useful. And so, cool, by fixing that, our service now looks like this. Go112 doesn't look appreciably that different from Go111. And while it was kind of hard to ultimately verify that this made out-of-memory conditions less likely, we could prove that in smaller scale tests that it actually did work. as intended. And it actually did avoid using quite so much memory, which was great. Okay, so going back to our policy again, there's still some problems here. And to really illustrate that, I want to look at another pair of scenarios. So here's one scenario. We get some short spike in memory use. So on this graph, we have memory on the y-axis and time on the x-axis. And so you can see that we'll have to wait 5 minutes before we're not charged for the memory from that heap spike anymore, right? So the yellow line is the actual amount of RAM used, whereas the blue line is the amount of memory that the runtime needs to, hold all the application's data. And because it takes so long to return memory back to the OS, you could be waiting up to 5 minutes. And so if you're the only application on a machine, then this isn't so bad, right? Because you have that machine anyway, it's dedicated. But in the cloud, you actually pay for this. And also, if anything else is running on your machine, then you increase the risk of the OS thinking that you're going to be out of memory, even though you're not actively using this memory. It's even worse if your application is bursty. You get these sort of regular heap spikes. And if the average period is less than 5 minutes, you might never try to return memory to the OS at all, right? You could be spending 95% of your time using the OS thinking you're using way more memory than you actually are. And one might think that, well, you said there's a cost to returning memory to the OS, so maybe we want to keep this around because we know we're going to use it in the future. But remember that 5 minutes is an eternity in CPU time compared to these costs. I promise you, it's not worth it. So let's take a bigger step back. Firstly, I think this rule has to go. One of the reasons we require a page to be unused for 5 minutes before we can release it to the OS is because scanning the whole heap is really expensive. We can only afford to do that every few minutes. So let's instead do it in the background, gradually and at a fixed rate. And so why fixed? It's easier to reason about and avoids us having to drop a whole lot of memory quickly at once, right? We can just take our time and steadily return memory to the OS. This also lets us bound the amount of CPU overhead that we use in returning memory to the OS. So this fixed rate can be set such that we don't use more than, let's say, 1% of your application CPU time. But the thing is, we know that this 5-minute rule is arbitrary, and the largest first policy fits kind of with the best fit allocation policy, like I mentioned earlier, and I'll get to that more in a bit. But it's largely motivated by efficiency with the OS that's trying to amortize these costs. So let's try to think of something better. Ideally, we want to come up with something where the right answer seems to fall out naturally. Like we could pick as an example of what isn't natural, is we could pick a smaller threshold. Instead of 5 minutes, we do 2 minutes. But that's just as arbitrary, right? We could pick least recently used. But the problem is in our allocator, we don't make any guarantee that we're going to reuse the most recently used memory, only a mild effort. But we know we have a best fit allocation policy. So can we leverage some property of best fit to know which memory we're unlikely to use in the future? So best fit, what does it prefer? It prefers smaller blocks. So maybe largest first is the right answer because we're going to try to get the smallest blocks first. But note that I mentioned earlier we're now tracking returned and unreturned memory separately. Specifically, this means we can't allocate across the two, and so that means we have to pick the best fit among the two if we want to maintain sort of a global best fit. But if we end up at some point picking the best fit from returned memory, then it's going to have more progressively attractive memory for that policy. So if you think about it, let's say we take some memory from the returned portion and we cut out a few pieces of it. Now that is smaller, and so now we're more likely to use the returned memory. So this doesn't even seem to fit very well at all with, trying to predict what memory the allocator is going to use. So maybe best fit isn't such a great idea. But there's hope here, because there are other allocation policies, and some of them tend to work just as well. One that I put up on the slide here is address ordered first fit. The idea is that instead of taking the smallest block that fits the allocation, we take the first one that fits by address. So by lowest address to highest address, virtual address specifically. And so both of these policies can be implemented with trees, so it's fairly easy to implement. And we know from various papers that their fragmentation behavior is very similar. Funny enough, nobody actually knows why first fit works just as well as best fit. It kind of defies intuition. Best fit makes sense, right? You want to try to minimize waste as much as possible, but first fit, it's just kind of consistent, right? But we know in practice that they work just as well. But the really neat thing about first fit is that it suggests a really clear scavenging policy. Return memory by picking memory by the highest address first. We know that this policy, the address ordered first fit, is biased against high addresses, so it's just unlikely to use them. Simple as that. And this works well even if we're tracking the memory separately. If we at some point choose to allocate from return to memory as a result of this policy, it doesn't make that memory more likely to be used by the allocator. And so basically the fact that it remains unlikely stays true because it's at a high address. And since we're picking high addressed memory first, the allocator is less likely to choose that. And so this fits really nicely. And first fit also coincidentally has this property that larger contiguous free spaces tend to aggregate higher up in the address space. And so we end up getting most of the efficiency benefits and amortizing the costs too. That's great. So highest address first, but is there a point at which we know to stop, right? Do we just keep taking the highest address first ad infinitum? Do we ever stop? Do we know what's definitely going to be reused? And so there is an answer to this question, but instead of thinking about memory like a human, we need to think about it like a GC to understand what the answer is. So the Go garbage collector views the world kind of like this. At the start of a GC cycle, it knows how many bytes of objects are live. And what this means is bytes of objects that are reachable. I'm not going to go into detail on what exactly this means, but you can just sort of think about it as the amount of memory that your application is actively holding onto. And that hasn't necessarily been freed yet. And so that's what this yellow line is. This yellow line is objects that might be free, but we don't know yet. It's just the amount that the garbage collector thinks your application is currently using. And so the GC then sets some goal. And this goal is based on GoGC. So specifically, it's the amount of live memory at the end of the previous GC times GoGC over 100, because GoGC is a percent expressed as an integer. Okay, so the application, and that is the red line here. So the application allocates up to that goal, and at some point in this time, the garbage collector remarks how much memory is live, and then it knows how much memory is live, and a new GC cycle starts. It starts all over again, and we have this line, the yellow line drop. Note that the y-axis here is actually bytes in objects and not RAM used. The Go garbage collector doesn't care about stuff like fragmentation or other factors. It assumes they're constant, and that it can basically, because it's much easier for it to just track bytes in objects it thinks that the application is using. So then we can continue this pattern, and when the amount of live object bytes doesn't change, we call this the steady state. Though regardless of whether we're in a steady state, we know that the garbage collector is going to let the application allocate up to that goal before the next garbage collection cycle starts. So that means we want to make sure that memory is kept available and not or rather at least that much memory is kept available and not returned to the OS, because then reusing it has a cost. And on top of that, we need to provide some headroom because, again, the garbage collector's goal number here doesn't include stuff like fragmentation, but we're thinking about pages here. And pages absolutely do include things like fragmentation. These are it's like the problem here is it's almost like a unit mismatch. And so we need something to bridge that gap. So we just picked 10% because this number is very variable. But we picked 10% headroom because this works well in practice. So we want to keep 10% more memory than we know that the heap is going to use in the near future. So this actually works really great. A small local test shows a very quick and relatively cheap recovery from a big heap spike. And this works well for multiple spikes too. In practice, we've seen pretty big savings from Kubernetes and internally at Google, between a 10% and 20% decrease in average memory use, which is really great. The takeaway for you, the audience, is that this is what you should expect from the Go runtime in your monitoring. If your application experiences a big heap spike, then the amount of physical memory your application is using should gradually go down as the runtime kicks in. If not, file a bug. That's definitely bad. There are still some problems in this space, but it's going to take a lot more background to get to it, and this works really well so far, so maybe a future talk will get to that. But what about CPU usage? This all must have some cost. I alluded to this, that we can bound the cost earlier, but this must have some cost, right? And yeah, of course, it wasn't that easy. So Kubernetes got a lot worse in Go 1.12. And then I made the same mistake in Go 1.13. And then on top of that, I got a 15% regression in gRPC throughput on like a large message benchmark that's sort of reusing pages really quickly. And funny enough, none of this was actually a direct consequence of any of the rules I mentioned earlier. There's just something subtle about when we ask the OS for more memory rule. Like, in particular, you could consider the reuse of returned memory as asking the OS for more memory. And honestly, this would happen pretty frequently compared to asking the OS for more memory, for more virtual address space in particular. And so doing that on the allocation path turned out to be a problem. And I confirmed that was definitely a cause, but why the regression was so large was really hard to understand. The costs that I've been talking about so far are like on the order of microseconds, whereas the problems I'm talking about here are on the order of milliseconds and seconds. So it turns out that there's been a bottleneck lurking in the runtime for quite some time. And to understand why, let's move on to part 3. Coming back to our home base, when I mentioned the tree earlier, the sort of pool of free pages, I was talking about this part of the diagram, managing free memory. Right, so what went wrong? It's related to that tree in some degree. Specifically, that tree is protected by a global lock. This is deep in the allocator, so conventional wisdom suggests that that using a global lock here shouldn't be a big problem. This code path doesn't get run on most allocations. Except I checked and I had evidence that this lock was collapsing. So I'll get to what that means in a sec, but it was worse performance, and it's not just because of my work. I could prove that this was happening since at least Go 1.11. So, okay, fine. What does it mean for a locks to collapse? Contended locks are slow, but things can get a lot worse than you might expect. And here's what I mean. The way a lock works is that multiple threads or goroutines race to try to acquire some value in memory. And if they fail to acquire that value, like set it to 1 or 2 or some value, then they go to sleep, to be awoken by the kernel or the Go scheduler later when the lock is released. On the left-hand side of the screen, you have runtime.mutex, the lock implementation used by the allocator. It's the bread and butter lock in the runtime. It's simple and optimized for the uncontended case. Basically, if someone comes in and notices the lock is unlocked, they'll just grab it, even if someone is already waiting for it. So the more parallel threads you add, the more the more any one of the sleeping ones can be delayed, because other ones will come in and stomp on their attempt to get the lock. And the more threads you add, the higher this becomes. So individual locking operations become more expensive with each new thread. And you get this nice mountain shape where every new thread that you add actively makes performance worse. On the right-hand side, you have sync.mutex, which works the same way when it knows that there aren't many coroutines vying for the lock. But it has an additional mechanism for when it knows that it is contended to stave off this sort of collapsing behavior. That is, if a coroutine is waiting, the unlocker, the coroutine that's unlocking will hand it off directly to a waiter instead of letting someone just come in and stomp on those requests. And it'll try to do that in order of those who came to try to acquire the lock. And so the result of that is that instead of performance collapsing, it just sort of levels off because the cost of each locking operation is basically the same. Even though the queue is getting bigger, it's not that cost is relatively low compared to this sort of constant stomping. And note that I said that runtime.mutex operates on threads and sync.mutex operates on coroutines. And this is the crux of why we can't just use sync.mutex. If it has better behavior, why not just use it? This is the crux of why we can't use it in the runtime. We've been considering making runtime.mutex not have this behavior, but it's slower in the common case to have this, and it's not trivial to implement, especially in the runtime, things operate on a much lower level, so it's trickier. It's trickier to get this right. So for a real world example of collapse, I ran a micro benchmark of 1 kilobyte allocations, which hits this allocation path reasonably hard. And you can see as we add parallel workers, performance slowly gets worse. In fact, slightly worse by like 30 or 40 cores or so, than if we just done it completely serially with only one core. One core, one thread. I'm using processors and threads here interchangeably. So without reading a ton of concurrent algorithms papers and changing runtime mutex to be non-collapsing, what can we do? So the key idea here is caching. Why grab the lock at all? Looking at some data from various Go applications, I found that most allocations are small, like one page exactly in size. And then this is allocations to that free pool of pages. Okay, so great. Yeah, let's add a cache. Just grab the lock once, get a bunch of pages, and then keep that in a processor local cache where we don't need any synchronization. Then we can just get it. And we have our pages without locking quite as often. So let's diagram what that might look like with this tree that we have so far. We have some global set of nodes, and we have the heap down below here. I've elided the released parts of it just for simplicity for now, because that's tracked separately at this point. So all these nodes reference some free part of the heap, and we get arrow spaghetti. So now when we allocate to the processor local cache, we take some of these nodes. But then what happens when we want to allocate from this cache? We basically have like a processor local tree here. We just have another tree. So if we want to be able to access these efficiently, so we need to split the nodes, do insertions, and the problem with this is that modern CPUs, like CPU architecture, is all about speculation, for better or for worse. Walking a tree is hard on a CPU because it's hard for the CPU to predict what's going to happen. At each node, it has to decide, okay, are we going to go left or right? It's hard to say. Where will the next node be in memory when you try to access the left or right node? Who knows? After a shuffling, after a bunch of insertions and deletions, the nodes get shuffled around and they could be anywhere, right? So it's not going to have good locality. And so one idea here is that, we could, instead of having these nodes in our tree at all, we could keep this in a list in the processor local cache. But this is still kind of expensive. It would probably still win out scalability-wise, but I tried this out on a small scale and it really wasn't great. And it's also trickier than you might think to implement correctly because you have to manage these intervals of contiguous free pages. So I looked for something simpler. Okay, so CPUs don't like trees, and this doesn't seem like a great fit. So let's think bigger. What do CPUs like? They like predictability, linearity. They like to mess with bits. So what about a bitmap? We use them all over the runtime for exactly this reason. Great. So here's a novel idea. This fits well with the fact that we have a first fit allocation policy now too, because that's the easiest policy to implement with a bitmap. So let's try a bitmap. To give you an idea of what this means and what this looks like, let's walk through an example of using a bitmap to manage pages. On the left-hand side, we have our bitmap, 1 bit per page. 0 means free, 1 means in use. The white arrow is where we start allocating from. And the invariant of the white arrow is that all memory before it is always in use. Okay, so let's allocate 1 page and see what this looks like. And it looks like that. We set the first bit, compute the address for that page, and return it. And now our state looks like this. That's how we do the allocation. To really sort of nail this down, let's try to allocate 10 pages. And there you go. You just set the next 10 bits. And if you're familiar with allocator terminology, it works almost like a bump pointer allocation. And finally, what happens when we want to free a page, specifically one that's before the white arrow? Well, we have to move the white arrow back to keep its invariant. Great. So that's how that works for the bitmap. But we want to cache some pages. So how do we do that? What does that mean? What does it mean to cache some of these? Well, the idea is here is that we cache some chunk of the bitmap. We have some global bitmap with, in this particular example, with 32 bits and thus 32 pages. And we want to cache some pages. The processor local bitmap is smaller by design and is empty when it has no free pages. So we always take from the chunk where the white arrow is, and we want to move this into the processor local cache. And we do it like that. We set all of the free pages in the global bitmap in that chunk to in use so that nobody else can use them. We sort of claim them. It's like land grabbing in a sense. And we move those bits into the processor local cache, so now we can just allocate it fairly quickly just using the same usual bitmap stuff, bitmap operations. So note that we had to move the white arrow forward in the global bitmap because we marked all of these as in use. Okay, so this works great for 1-page allocations, but you might have to search the whole bitmap to find n contiguous pages. And that scales a lot worse than a tree. Trees are logarithmic generally, and this is going to be linear in the size of the heap. So can we do better than that? Well, if the answer was no, I probably wouldn't be going this far with it. The main idea here is to summarize chunks of the bitmap. This is useful in and of itself for skipping large swaths of in-use address space. So let me demonstrate the summary scheme. Each bitmap chunk is given 3 numbers: start, max, and end. Start is the number of free pages on the left side, end is the number of free pages on the right side, and max is the largest block of contiguous free pages in the bitmap. So hence the summary we see here. The beginning has, the left side of the bitmap has no free pages, starting from the left side. The right side has 1 contiguous free set of pages. And in the middle, you can see that they're the largest space of contiguous free pages is those 2 zeros in the middle there. And that's the start, max, and end that we get there. And so we can summarize the other one much the same way. There's 4 0 bits at the start, so start is 4. There's 3 0 bits at the end, so end is 3. And the max happens to be the start in this case. Max is any contiguous block of free pages in that bitmap. Okay, so if max is 0, then we can skip over this part of the bitmap and thus this part of the address space entirely. This makes finding free pages faster, but it still doesn't scale well. Well, then what are start and end for? Well, that's the trick here. We can build a tree out of these summaries. We can compute a summary for this whole bitmap just by merging these summaries. I'm not going to walk through the whole algorithm, but it's pretty straightforward. You can see here that there's one summary for this entire set of 32 bits, and you can sort of see how the properties of the 2 summaries funnel up into this top summary. Reverse engineering the exact algorithm for building a tree out of these and merging summaries is left as an exercise for the reader. But wait, hold on. Didn't you just say trees have problems? Yeah, but this tree is different. The bitmap is indexed by address, and so are these summaries. So each summary layer can live in one big array that we map in on demand. Like, note that these summaries are sort of adjacent to each other, and if we have one big array of them, and we know the address that we're going to look at next, we can simply compute which summary we need to look at, and then eventually which part of the bitmap we need to look at. And we don't need any pointers, right? This can be all just indexing math. So, better locality. We don't need to worry about the CPU mispredicting some things. And because it's all sort of linear and contiguous, when we iterate over it, the CPU is going to be able to do this pretty predictably. Also, we can merge more than just two summaries together at one time. So plus the sort of, if you're imagining the way this indexing works is, this tree sort of covers the whole address space up front. So the depth here is fixed, right? The usual tree has sort of variable depth based on how it's balanced, but this one, it always has a fixed depth. So in practice here, we have around 5 layers of these summaries, and compare that to having to walk 20 pointers of a tree for a big heap. Of a more conventional tree for a big heap. Great. So this scheme rolled out in Go 1.14, and we saw some big improvements in allocation-heavy web service benchmarks, running with a lot of cores. Up to 30% improvement in throughput and 20% reduction in the tail latencies. And stepping back to our 1 kilobyte allocation throughput microbenchmark, it works a lot better. This microbenchmark is somewhat unrealistic, so that's part of why it doesn't just, scale up very smoothly. But now we're no longer collapsing, and that's really what we were after. It also turns out there's a scalability bottleneck, which is the other reason why it doesn't just smoothly go up, but that was actually fixed in Go 1.15. So this graph looks even better for Go 1.15, but unfortunately I don't have the data for that. The takeaway from all this for you, the audience, is that the Go allocator just scales a lot better now. If you're previously limiting the parallelism of your application because of the Go runtime, you don't have to anymore. This situation is much better than before, and it's improving constantly. There's always things that are making the page allocator better and better with each new release. But I couldn't leave you without one more bug, and this one's fun. It turns out I made the allocator too fast. Yeah. What does that mean? Well, remember, we have a GC in Go. And unsurprisingly, by allocating at a higher rate with these more cores, we're putting more pressure on the GC. And there's like a complicated chain of reasons here involving the GC's feedback loop as to why, but the end result is that we could have an unbounded amount of additional memory used, basically proportional to how hard we were allocating. In practice, I saw almost twice the amount of memory being used as a result of this problem. Luckily, this could be fixed by bounding a parameter in the GC's feedback loop, but it does mean that now the GC is free to push its utilization higher if the application is allocating really hard. In practice, though, we're allocating so much faster that even though the GC is working harder, this is still a large net win. And so we also want to bias toward using less memory because it tends to be a very fixed resource, whereas CPU usage is a bit more flexible. And we've reached the end. If there's anything you take away from this talk, here are my suggestions. Firstly, memory management is like an onion. Layered, complicated, and sometimes makes you cry. And we mostly talk about the deepest layers here. Specifically, the Go runtime, as of Go 1.13, gradually returns memory to the OS. Specifically, it returns the highest address memory first while leaving headroom for the application. What this means for you, again, is that Go applications should use less memory and should expect better recovery behavior from heap spikes, or in other words, it's more robust. Expect to see this showing up in your monitoring, and if not, please file a bug. That would be bad. That means that this that the runtime isn't doing its job. And then, as of Go 1.14, Go's memory allocator scales better than before. It accomplishes this by managing pages in a summarized bitmap. The key point of the bitmap is it allows us to cache pages in a very intuitive manner for lockless access. What this means for you, the audience, is that the Go runtime, specifically the allocator, scales better to many cores. So don't limit your parallelism because of the allocator. Just blast it. And I'm sure we'll find another bottleneck, but just blast it. And finally, more people should talk about these deep layers. Approximately no two allocators return memory the same way, which seems to imply that none of us know what we're doing. Simultaneously, it seems like approximately everyone except us now manages pages the same way, with a big old tree. And that seems to imply that we've all fallen into a rut as a community, and this deserves some re-examining. And that's all I have. Thank you. I'd like to thank the whole Go runtime and compiler team. Thank you so much, and thank you for watching. I hope this was useful, informative, and at least a little bit of fun. Even just the schadenfreude of laughing at my laughing at my hilarious failures. Thank you.